Okay, picture this for a second. Imagine you take an absolute novice, someone who barely grasps the basics of a subject, and you ask them to teach a really complex, profound new skill to a literal genius. I mean, it sounds completely backward, right? Kind of like a paradox. But what if I told you that in the wild world of cutting-edge artificial intelligence, this isn't just some weird thought experiment, it is actually the key to unlocking the next massive leap in how we train large language models.
So, welcome to The Explainer. I am super thrilled you're tuning in today because we're going to be unraveling a truly fascinating July 2026 AI research paper out of Tsinghua University and ByteDance. It's called Weak to Strong Generalization via Direct-on Policy Distillation, and honestly, it solves what might literally be the single biggest economic and technical bottleneck in the entire AI industry right now. We are talking about a total paradigm shift here, and we're going to break the whole shebang down step by step.
All right, let's dive right into this with Section 1, the AI training bottleneck.
So, to make AI models truly capable of deep, logical reasoning, developers use a technique called reinforcement learning with verifiable rewards, or RLVR. Think of it as the secret sauce that makes top-tier AI so incredibly smart. But well, here is the massive compute crisis we're facing. To actually learn, the model has to generate thousands upon thousands of its own internal thought processes, which are called rollouts, during training. Essentially, it tries to solve a problem, gets graded, and then updates its brain. Now, imagine trying to do this with a model that has hundreds of billions of parameters. Every single update requires that giant, heavy model to generate its own super slow, incredibly costly rollouts. We are talking about burning through literally millions of dollars of GPU compute just to teach it one single new trick. As these reasoning models get bigger and bigger, rerunning this reinforcement learning from scratch for every new model isn't just expensive, it's threatening to make post-training an impossible bottleneck.
Which naturally brings us to Section 2, the flaw in copying. If training the big model is way too expensive, you're probably thinking of the obvious workaround, right? Why don't we just run the training on a small, cheap model and then just copy its brain over to the big one? Well, to understand why that totally fails, let's use a quick metaphor. Imagine a middle schooler who is just an absolute chess prodigy. They are trying to teach a brilliant college math professor how to play chess. If the professor learns by simply copying the middle schooler's entire brain, which, includes their limited vocabulary and middle school math level, the professor would suddenly forget calculus. In AI terms, if a massive student model just blindly copies the final output of a smaller, weaker teacher model, it actually overwrites its own advanced capabilities. Sure, it absorbs the chess skills, but it also absorbs the middle school limitations.
And this brilliantly illustrates exactly what goes wrong. If you look at how vanilla on-policy distillation works, which is the old way of copying, it's a bit of a disaster. Say we have a highly capable student model, like R1 Distil 7b, starting out with a reasoning accuracy score of 56.7. But when it tries to imitate a weaker 1.5 billion parameter teacher model that just finished RL training, the student's performance actually gets dragged all the way down to a 50. It's literally imitating the weaker teacher's limitations. It's basically losing its PhD just to learn a new trick. So how do we fix this? Let's move to Section 3, extracting the policy shift. If we can't just copy the teacher's final product, what's the alternative? We transfer the direction of improvement. This is where the researchers introduce this genius concept called policy shift. Instead of looking at the small model's final, post-RL brain, they look at the mathematical difference, specifically something called the log ratio, between the weak model before it was trained and after it was trained. By subtracting what the weak model already knew beforehand, they strip away all of its intrinsic capacity limits. What you are left with is just the pure, isolated direction of what the reinforcement learning actually changed. It's a dense, implicit reward signal. It tells us exactly which actions the RL made more likely and which it suppressed, with absolutely none of the weak model's baggage. So here is the beautifully elegant recipe they created, called Direct-OPD. Step 1. You run your expensive, slow reinforcement learning, where it's incredibly cheap to do so, on a small, weak model. Step 2. You compare the pre-RL and post-RL checkpoints of that small model to measure that pure mathematical shift we just talked about. And finally, Step 3, you apply only that specific shift to the larger, smarter model's own thoughts. Going back to our chess metaphor, the math professor doesn't copy the middle schooler's brain. Instead, the professor plays their own game of chess and simply gets a pure signal, like a thumbs up or thumbs down, based on the direction of the middle schooler's strategic improvement. The big model learns the chess strategy without losing its math PhD. It's brilliant.
Now, an elegant theory is great and all, but does this actually hold up in practice? Let's jump into Section 4, Weak Teachers, Strong Students, for the big reveal. So the crucial point here is this massive number. Using Direct-OPD, the researchers took a Quen 3-1.7b student model and boosted its accuracy on the notoriously brutal AMIA 2024 math reasoning benchmark by a staggering 10 full points. I mean, it jumped from 48.3% to 58.3%. And remember, this was achieved by transferring the implicit reward from an even smaller, heavily constrained 1.5 billion parameter teacher model. No way, right? But it works.
And, it wasn't just a fluke. The gains are incredibly consistent across the board. The QN34B model jumped 5.1 points. The R1 Distill 7B jumped 6.4 points. What's truly wild about this is that it works even when the student model starts out inherently smarter than the teacher ever was. The paper proves that Direct-OPD doesn't require the student to just blindly imitate the teacher's top tokens. It allows the large model to keep its high-capacity thinking patterns while absorbing the newly learned reasoning direction. It's cross-pattern transfer at its absolute finest. Which brings us to the real-world impact in Section 5, the compute cost advantage.
Why are developers and tech giants going to care so deeply about this? Well, it comes down to massive savings in time and money. Now, what's really interesting about this is the incredible efficiency on display when comparing wall clock time. Doing direct reinforcement learning on a big 7B model is a volatile, wiggly process that literally takes forever. But the Direct-OPD weak-to-strong transfer, it achieves superior accuracy in just a fraction of the time.
Let's put some hard numbers to that. If you try to run Direct-RL on the R1 Distill 7B model, it takes approximately 320 hours using 32 highly expensive A100 GPUs. But if you use the weak-to-strong Direct-OPD method, you run the RL on the cheap 1.5B model, which takes about 160 hours. Then the actual transfer phase, injecting that knowledge into the 7B student, takes a mere 4 hours on just 8 GPUs. You get the exact same or even better performance while virtually cutting the massive compute bottleneck in half. That is a game changer of an efficiency gain.
And as if solving the compute crisis wasn't enough, the researchers introduced one final technical breakthrough in Section 6, stacking new AI skills.
Think about building the ultimate AI student. Because Direct-OPD transfers a pure signal rather than just overriding the whole brain, you can use something called sequential composition. Basically, you can train a large student model with one RL shift from one cheap teacher, let's say a logic skill. Then you can immediately stack a completely different RL shift from a completely different cheap teacher, like a math skill, right on top of it. The student just cleanly accumulates these distinct gains. It essentially turns AI post-training into a system of modular building blocks, where independent, cheaply discovered skills can be endlessly stacked onto one mega student.
I really want to highlight this exact quote directly from the researchers because it perfectly summarizes the entire paradigm shift of this paper. They wrote, RL outcomes can be reused across model scales as implicit reward signals, not merely as final models to imitate. We have to stop thinking about AI training as just copying a final product and start thinking about it as extracting and transferring the mathematical trajectory of learning itself. Which leaves us with this final, kind of provocative thought. If Direct-OPD means that literally any new reasoning capability or AI skill can be distilled by a tiny model into a cheap, universally transferable module, what does the future frontier of AI look like? Are we moving away from training massive monoliths from scratch and toward a future where mega models just download cheap, specialized skill shifts on the fly? It's a completely fascinating vision for the future of efficient AI development. Thank you so much for joining me on this explainer today. I really hope this helped you grasp exactly why Direct-OPD is such a massive breakthrough. Keep questioning, keep learning, and I'll catch you on the next one.